So I would like to thank the organizers, to thank Peter and Helmut and Enrico for inviting me to give this talk in memory of somebody I guess all of us greatly admired, Jean Bourgain. This is a picture of Jean Bourgain, of Jean, from the Institute website. I'm not sure if I'm breaking some copyright rule or something by showing it to you, but I figured out that since it's an Institute webpage, I could show it here at the Institute. But I actually don't need to steal pictures from the Institute website. I've known, Bourgain was a close friend of my father, Elon Lindenstrauss, who passed away maybe 7 years ago. And he would come to our house occasionally for dinner. There was a year he was in Jerusalem, so he would come quite often. And so I took some pictures, or more precisely, my mother found for me some pictures from the family album to show you. So this is Jean Bourgain in Oberwolfach in '86. This is Jean at Urbana-Champaign. I think this is around the time he learned how to drive and was quite happy with this new skill. And this is a picture that actually I think was featured also yesterday at dinner of Jean with my father on Wolfgang's. There were actually 3 additional pictures yesterday from our family collection that were on display, but I don't think you would guess which ones they were. So anyway, you could try. So I'll start with the mathematical part of my talk. So when I was here as a postdoc between 1999 and 2001, Bourgain mentioned to me a conjecture that he thought might interest me, which was sort of not so far from the things that I was thinking about at the time. This is a conjecture of Erdős and Volkmann from around '66, that any Borel measurable subring, so any subset of the real line which is Borel measurable and in addition is closed under addition and multiplication, is either everything or it has 0 Hausdorff dimension. And this was indeed similar to things I was thinking about at the time. So for instance, one theorem which sort of I know well and was sort of very influential on me is the theorem of Rudolph, which says that any locally finite Borel measure mu on the real line, which is additively invariant under the integer. So you can think of it, if you wish, as the probability measure on R modulo Z. And multiplicatively invariant under 2 relatively prime integers is either Lebesgue or has dimension 0. So this conjecture was proved in 2001 by Edgar and Miller, and the proof relied heavily on Mastran's projection theorem, a classical theorem about projections, which is well known, that if I have a subset, a nice subset of the unit square, then for almost every direction, the projection of the set is the largest it can conceivably be. A subset of the line would have a hard time having Hausdorff dimension bigger than 1. And in addition, it's easy to see that the Hausdorff dimension can only decrease under Lipschitz maps. So this is the most it can reasonably be. And the theorem of Mastran is that for almost every theta, this easy upper bound is actually inequality. And if the dimension is bigger than 1, you could actually say something more. You could say that the projection has positive Lebesgue measure almost surely. I think I've never looked at Mastran's original proof. It is said to be quite intricate. Kaufmann gave an elegant proof of Mastran using energy characterization of Hausdorff dimension, which is what most people use. Using this theorem, Edgar and Miller showed that indeed the conjecture is true, because if you had some subring which has positive dimension, then by the theorem you could find some n tuple of real numbers, so that S1R plus the sum set of S1R up to SNR would be everything. Okay, so if you could do that, you could do that with a minimal number of S1 to Sn. If n is minimal, this gives me an isomorphism of R modules from R to the n to the real line. So if it's an isomorphism, I can take its inverse. The inverse would give me, and if I take the inverse and ignore all coordinates except the first coordinate, I get a Borel measurable map from the real line to my ring that has to be linear. But I mean, a Borel measurable linear maps, there are not so many of them, so this ring has to be everything. So this is the full proof, more or less. And fortunately, Bourgain was not aware at the time of the Edgar Miller work. And so he gave his own proof, a different proof, following a much harder route. I mean, sort of it's a much harder route, a discretized approach suggested by Katz and Tau. But as you would see, this harder route has its advantages. So let me give some notation. The set is delta separated, a subset of the real line, or symmetric space is delta separated if the distance between every 2 points is at least delta. I would often look at the covering number of a set A by delta intervals. So up to minor things, right? If I have a set which is delta separated, this covering number would just be the cardinality. And I would also need a notion of regularity. So if I have a set, a delta separated set A, I would sort of be rather unhappy if all of it was bunched together on a small corner of the space. So I basically want the number of points to decay on small intervals. So how small? Well, I mean, I guess if my set is delta separated, there's no sense in looking at things smaller than delta. And you start with some scale, and then you want that for every interval of size in the scale, the number of points in the interval is the number of points in my set times some power of R. And then the theorem that Bourgain proved, which verified the conjecture of Katz and Tau, is that for any sigma and kappa, there are some epsilon and capital delta, and capital delta is some kind of size increment. That's somehow what we gain. So that if I have a set which is delta separated in the real line, with at least delta to the minus sigma points, and is kappa regular starting from some scale, you could take the scale to be polynomial in delta, then either A plus A or A times A has a larger covering number by delta balls than my original set. Okay, this is somehow my gain. So the two parameters here, sigma and kappa, and both can be thought of as some sense as measuring some kind of discrete notion of dimension in slightly somewhat different ways. And the theorem gives a dimension increment. Now, this is formally analogous to a well-known result of Erdős and Semeredi, which Avi mentioned yesterday in his talk, that if I have any subset of the real line, either the number of elements in the sum set or the number of elements in the product set has a power increment over the number of points in my original set. An elegant proof of this using the Semeredi-Trotter incidence bound was given by Elekes and gives the explicit value of mu equals 1/4, which has since been improved. The conjecture is that you could improve this mu all the way up to anything smaller than 1. But that seems to be open. But the key difference between what Erdős and Semeredi proved and what Bourgain proved is that they don't control how close the points are. If you actually work through the Elekes proof, you can get some kind of discretized version. You could basically, starting with a delta separated set A, you could get an increment of the number of points at a scale delta squared. But this passage to a smaller scale is not something that fits well with the kind of bootstrapping arguments that Bourgain used his theorem for to great effect. So here, this is just to remind you what was in the previous slide, definition of regularity. I like to think of Bourgain's discretized sum product theorem as a theorem not about sums and products, but about projections. I like projections. So here's another variant of this result by Bourgain. Again, so sigma and kappa, some types of dimension-like quantities. So I have a subset in the square, which is delta separated, and a set of directions, which is delta separated, which are both k-regular. And the number of points is at least delta to the minus 2 sigma. Then there is a direction where when I project, the number of delta intervals needed to cover this projection is bigger than the square root of the number of points. It's delta to the minus sigma minus delta. Now, if you want to work out the equivalence between this theorem and the sum product theorem, it's not, okay, that's something to do. I mean, basically, key ingredient here is Balog-Semeredi-Gavor's lemma. That itself is best thought of as a theorem about projections, about sets which have 3 small projections. So this is again Bourgain's projection theorem. And so if I have 2 directions which are separated by some reasonable amount, and I take my set A and project in these 2 separate directions, so it can't be that I can cover both of these directions by very few delta intervals, because then I could just cover the whole set by a very small number of small parallelograms, which are essentially can be covered by a fixed number of squares. So this half here, this is a trivial thing, which gives me delta to the minus sigma, and the punchline is this extra delta in the exponent. This theorem implies a theorem about Hausdorff dimension of projection, which I think is strictly stronger. So I think this corollary is strictly less, contains less information than the theorem, but the corollary is something which is easy to digest. It just says that if you have a subset of the Borel subset of the unit square and some set of directions, and if the dimension of my set is at least twice sigma, and the dimension of the set of directions is at least kappa, then at least for one of the directions inside my set of permissible directions, I would, one theta in the set of permissible directions, the projection would have dimension which is bigger than half the dimension of the set I'm trying to project plus delta. As a corollary, so this is this corollary about Hausdorff dimension, and the corollary of the corollary is that the Erdős-Wolkmann ring conjecture is true. Any Borel measurable subring is either the real line or has 0 Hausdorff dimension. And okay, I'll only show the weaker statement that the dimension is either 0 or 1. This is still somehow, you need to say something to go that if the dimension is 1, you actually the whole thing, and that's essentially something which was known at the time, and follows from a result of Falconer. It's basically one application of Mastron's projection theorem. Anyway, so various notions of dimension are usually not, they sort of have some kind of peculiarities what happens if you take a product set. You would like to say that if you take a product of 2 sets, the dimension adds, but somehow for most notions of dimension of arbitrary sets without additional structure, there's sort of always some strange phenomena. But here, fortunately, the things, sort of the pathology is working in your favor. So if you take a set R, this is my ring, and multiply it by itself, the Hausdorff dimension of the product will be at least twice the dimension of my original set. It certainly happens that you could have 2 sets of 0 Hausdorff dimension. When you take the product, you suddenly get something of full Hausdorff dimension, but at least twice the dimension of what you start with you'd get. And now you take E to be this product set intersected with some large square, just because in the statement of the projection theorem of Bourgain, I assume that my set E is bounded. And take a direction of set of directions basically determined by my set R. And applying the Hausdorff dimension corollary of Bourgain's projection theorem for a particular special case of sigma equals kappa equals the dimension, Hausdorff dimension of R, I would get a dimension increment. I would get that there is some little r in my ring, so that my ring plus r times my ring has bigger Hausdorff dimension than my ring had. But that sort of doesn't make much sense, because the ring is a ring. So r plus little r times r is just my ring r. So I got a contradiction. maybe it'd be useful to compare Bourgain's projection theorem to the Mason-Kaufmann projection theorem. So Mason's original statements talked about almost every direction, but from Kaufmann's proof, Kaufmann extracted something a bit more accurate, that for any kappa smaller than the Hausdorff dimension of the set I want to project, the set of directions, so recall, right, I mean, Mason proved that for almost every theta, the projection would have dimension, the same dimension as E, or minimum between E and 1, but that's sort of somehow included that kappa is bounded from above with 1. So for almost every theta, you get here equality. The dimension of thetas for which you get strict inequality is at most kappa. Or maybe this is less or equal, I'm not sure. So if I want to get a direction for which the dimension of the projection would be at least half the dimension of my original set, to get anything non-trivial out of this Kaufmann-Mason theorem, I need to assume that my set of directions is at least of dimension half the dimension of the set I'm projecting. Bourgain's projection theorem gives you an entropy a dimension increment no matter how small your set of directions is. But of course, if you have a bigger set of possible directions, you could hope to get a bigger dimension increment. There are actually explicit estimates on how much entropy increment you could get by, or dimension increment you could get. One of them is by Hochman, Peter Varya, and myself, which we'll need to write up. One by Bateman and Lee, and one by Gus, Katz, and Zal, which is, the last one is available on arXiv. So it sort of seems people who see this for the first time would think, might be a bit surprised how even actually some experts sometimes are not completely obvious to them why the discretized version implies the Hausdorff dimension version. So I thought to give some hints how this works. So I'm going to lie a bit. That's sort of allowed when you give a 45 or 40-minute presentation. So this is a theorem, Bourgain's theorem of projection. I added one more bell and whistle that somehow, this bells and whistles comes automatically from the proof, that you could not just take one projection, but one direction, but basically outside a small set, all the directions inside B would be good for you for the projection. And you don't need to project the full set. If you pass to some kind of regularized subset of my full set, then any big subset of the regularized subset, this should be A prime, I guess. And here's an A prime. The projection of this subset of the regularized set is big. And okay, to make life simple, I'm going to sort of ignore this distinction A and A prime. So I'm somehow just, I didn't promise an actual proof, just some kind of indication how this works. So I'm assuming that my dimension is at least twice sigma, and the dimension set of projections is kappa. And how would I use this information? So the sort of a standard way to use Hausdorff dimension is to basically say that there's a nice measure on the set, a measure which decays at the right rate. It's called Frossman's lemma. Okay, this is a measure which decays like on the set E, like R to the twice sigma, and on the set B, like R to the kappa. And I'm assuming that all of the directions theta in B, my Hausdorff dimension of the projection is not as big. I get too small an entropy increment. Again, should be capital delta here. So that's one way we use Hausdorff dimension for the sort of measure we are projecting, the sort of the input measure. For the output measure, the projected measure, I use a different way of somehow exploiting this assumption of small Hausdorff dimension, and that's just a definition. By the definition, I can cover a set. The definition of Hausdorff dimension is given in terms of a cover by some collection of intervals. And if you work it out, I mean, I just, for simplicity, I assume, as I'm allowed, that all the intervals I use to cover my set E would be of dyadic size. And then I get by this assumption says that I have an efficient covering of my set. Now, the efficient covering has sets of various sizes, okay? It's not one size. But the point is, if I choose some sequence which is summable, like I to the minus 2, help? Okay. I to the minus 2, then at one of the scales, my measure, this is mu, sort of the measure adapted to E, would be at least I minus 2. Okay, so one of the basically talking, so this covers the projection. So I get, for one scale, I can cover a significant portion of the projected measure. So if I see what it means with the original set, the pi inverse of some small number of intervals or of size 2 to the minus I has large measure. And then this basically, if I sort of wave hands a bit and ignore this passage to a regularized subset, etc. So once I have big sets, by again using Forssman or something, I can extract big delta separated subsets that somehow just follows, because each delta interval has, by our assumption, a small measure, and then I could if I just take this A double prime, not the full set A, but this subset which projected to this set of big measure, then I get a big subset of A which projects to a set of small covering number, in contradiction to the discretized statement. So, okay, so this is somehow the discretized projection theorem of Bourgain. But the remarkable thing about this discretized projection theorem is how many applications it is, how powerful it is. And probably the most, certainly one of the most remarkable applications of this is regarding spectral gaps for averaging operators. So suppose I have some compact group and a symmetric subset. Symmetric just means that the inverse is equal to itself. And you can define the appropriate averaging operator. It's a self-adjoint operator from L2 of G to L2 of G. Norm of this operator is obviously 1, the way I defined it, and it fixes the constant functions. And this averaging operator will be said to have spectral gap if there is some C strictly less than 1, so that for any function which is orthogonal to the constants, the averaging operator decreases its norm by at least C. So this is not so obvious that such things should exist for infinite groups, right? I mean, certainly for any infinite abelian groups, like the circle or something, you will not be able to find any finite symmetric subset with a spectral gap. And Avi in his talk mentioned expanders. Expanders, there's no such thing as an expander graph, right? I mean, when you talk about an expander graph, you actually implicitly talk about a family of graphs, an infinite family of graphs which have a uniform spectral gap. That's an expander family of graphs. But a single infinite compact group with a spectral gap is an analog of an infinite family of expander graphs. Okay, sort of, it's in some sense infinitely many uniform spectral gap assumption for somehow infinitely many operators in some sense. So it's absolutely not obvious that such things should exist, for instance, in SO3, and it was actually in efforts to prove to solve the Ruzevich conjecture about averaging, about invariant means on the sphere, it sort of became a sticking point. But Drinfeld gave an example of a symmetric set with a spectral gap for SO3, and I think Sullivan and Margulis gave for higher dimensional spheres. And a very nice, explicit, optimal set of rotations, which has a spectral gap, was given by Lubotsky, Phillips, and Sarnes. They gave several, but this is one of them. You just take 6 rotations around the x, y, z axis, each one by a particular angle. And if you look at the norm of this operator, averaging operator from the L20, from the space of function orthogonal to constant to the space of functions orthogonal to the constant, turns out to be square root of 5/3, which is optimal. Now this relies on heavy machinery, right? I mean, this seems like you could draw the 6 rotations, this is boundary. Also, you could explain to an undergraduate. But to explain the proof of this, that sort of from the ground up, that would require some higher education. I mean, this uses, I think, quite a bit of sort of serious, profound work by Delin and, okay, this is heavy machinery. A more flexible proof of spectral gap was given by Gambo, Jacobson, and Sarnak, which was quite influential to what I will talk about in a minute. Still needed stringent conditions on the set you're averaging on. To continue, I need a definition which sort of makes sense. If I have a reasonable group and I have some symmetric subset of this group, maybe generating a dense subgroup of G. So this set is said to have good Diophantine properties if it sort of has a Louville-like theorem. Any word of length n in the generator, so I should have probably put here S1 to Sk, not G1 to Gk, right? Any word of length n in this generators, in these S1 to Sk, is either equal to the identity or is at least exponentially far away from the identity. So it's easy to give examples of that. If you take any linear algebraic group defined over the rationals, for instance, and take its algebraic points, any subset of the algebraic points has good Diophantine properties, essentially because of Louville's theorem. But it is not known, seems to be a hard problem, if, for instance, a random choice of symmetric subset of a compact Lie group, even SU2, which for my purposes, SU2 and SO3 are essentially the same group. For other people, Borel is not here, but I mean, somehow other people might somehow throw something at me. Anyway, it's not known if a random choice of symmetric subset would have good Diophantine properties. Kaloshin and Rodniansky gave something nice, but sort of much weaker stretch exponential bounds, so it's completely open. Anyway, theorem of Bourgain and Gambo. So I'm sort of stating 2 theorems. One is a special case of the other. A, because they appeared in different papers, and B, because somehow each one of these papers introduces sort of many new ideas, and I think they deserve being listed individually. So they show that if I have a subset of SU2, finite symmetric subset of SU2 generating a dense subgroup of G with good Diophantine property, the corresponding averaging operator has a spectral gap, which is extended to SUD. At least formally, they stated it in a slightly weaker way, that they assumed that my set of generators is algebraic, which more or less is the only way I know how to generate these sets of rotations with good Diophantine properties. And then they said that AS has a spectral gap, that's SUD. So the SUD paper is harder, and it's actually a paper which is quite nice to read. Following their general approach, Yves Benoit and Nicolas Desax proved that for any symmetric set S in a simple compact trilinear group with good Diophantine properties, the corresponding averaging operator has a spectral gap. So this is sort of a clean statement. Side note, we started this discussion by talking about Erdős-Volkmann ring conjecture. You could just ask, what about a group? Suppose I have a group like SU2 or SUD. In a non-commutative group, somehow this one operation of group operation is sort of has both multiplication and addition in some sense. And so Nicolas Desargues, using the ideas that Bourgain and Gambourg developed for the SUD paper, showed that any dense Borel measurable subgroup of G is either equal to the whole group or has Hausdorff dimension 0. So this is really analogous to the Ordish-Volkmann ring conjecture. The case SU2 is something that Nicolas Desargues and I did together. So what's the basic strategy of this Bourgain-Gambourg proof of spectral gap? I'm not going to give a full proof, but just general, how do you start, I guess? And a good starting point is this analogy between a spectral gap on a group for one set of generators on one group and a family of expanders. So I want to somehow, I'll prove separately spectral gap on pieces of the spectrum of the group. So Bourgain-Gambourg used a kind of Littlewood-Paley decomposition on the space of functions orthogonal to constants on the group G. So you write any, any function as the sum of Fn, where each Fn is basically f convolved with some function which is more or less, you could think of as a uniform measure on a ball around the identity of size 2 to the minus n, and you subtract what happens when you convolve on slightly coarser scale, twice the scale. And to make things nice somehow, to really be adapted to working in the space of constant functions, just take P1 to be the constant function 1. So I think of these functions Fn as functions that are interesting on scale 2 to the minus n. If I take much finer scale, then they're essentially constant. I would be bored. And if I take a coarser scale, it sort of fluctuates so quickly, I just won't understand what's going on. This function is interesting on scale 2 to the minus n. And essentially, these Fn's are orthogonal. If I really wanted to, I could make them orthogonal, completely orthogonal, but certainly the L2 norm of F is roughly the sum of the L2 norms of all of these Fn's. Now, to show a single spectral gap, basically, what Bourgain-Gambourg proves separately, that you have a spectral gap on these functions Fn separately. So each one of these pieces is treated separately, and to somehow prove the spectral gap, you apply a different power of my averaging operator to each one of these Fn's. So this is a reminder from the previous slide. I took a single function f, wrote it as the sum of infinitely many functions, which are interesting on scale 2 to the minus n. I have my averaging operator. And what they show is that for suitable constants c and alpha, if I look at Fn, I apply to it the averaging operator, some big constant times n times, then I would decrease the size of the function exponentially. And then, since A is itself a joint by basically the inequality of the means, if I have L less than K, I would get this kind of bound. So basically what you could conclude if I fix some L now, which is not dependent on N, that if I apply this fixed number of steps of the averaging operator on Fn, I decrease its size by some fixed amount. And if this fixed L is large enough, I would win over all of the implicit constants and get a spectral gap for the averaging operator. That's why I said that somehow, from my point of view, a spectral gap on a compact group is, of an infinite compact group, is essentially like a family of expanders. Yeah, let's say a few words before about how the proof goes. This will just be extremely superficial and brief, but so this averaging operator you could think of as being sort of a convolution with a uniform measure on the generators of the set S. And right, so here it should have been that sort of delta measure at S somehow disappeared. Don't know where it went. Maybe out looking for coffee or something. But so how do you prove something like that? So to begin with, you forget about these functions that you're trying to show decay. You start you basically start with working with this random walk measure, this uniform measure on this symmetric set S. And you take its convolution with itself, some little constant times n times. And okay, just because you're working at scale 2 to the minus n, it makes sense to convolve this with a uniform measure on a ball of size 2 to the minus n. And then you get some decay of L2 norm. You're basically using the good Diophantine properties of S. Once you assume, so this step is either very hard or very easy depending on how you look at it. If you assume good Diophantine properties of S, it's very easy. And if you don't assume, we don't really know how to do it except by using number theory. Then you do bootstrap. That's sort of, right? I mean, Bourgain was a master of many things, but one of them was bootstrapping. So you apply many times the discretized sum product theorem in conjunction with Balog Semeredi-Gowers, which I already mentioned, which is somehow the oil that greases the wheels of additive combinatorics or arithmetic combinatorics. Iteratively pass from some decay for taking this uniform measure on S, some small constant times n times, and then convolve with the averaging, with sort of the measure on a ball on the right scale I'm looking at, to almost optimal decay when I take the same measure and convolve instead of a little constant times n times, a big constant times n times. That's somehow where sort of the really heart of the proof works. That's the hard work, it goes here. And then there's an end game, which basically you do some last magic to conclude that even though you just got almost optimal decay, that's enough for you to win at the end. This last step, this end game for the SU2 paper, essentially Bourgain and Gambourg used what Gambourg, Jacobson, and Sarnak developed. For the SUD paper, Bourgain and Gambourg have a nice different alternative. I don't think there was anything wrong with the original Gambourg, Jacobson, Sarnak way, but there's a different way in the SUD paper. But the real novelty here is the bootstrap. That's somehow where systematic things happen. So I have maybe 2 more minutes before Enrico would want me to finish. So I'll just mention another application that I was involved with. So this is a theorem of Bourgain, Fuhrman, Moses, and myself. So suppose I have a probability measure on SLDZ. So the support of mu generates a Zariski-dense subgroup of SLD. You could relax that somewhat. And this measure has epsilon moments or exponential moments depending on your point of view. And now you take a point and you convolve it with this measure many times. So you take some kind of random walk by applying randomly a matrix in SLDZ. And the statement says is that this is a Fourier series statement, which basically says that if this random walk after n steps is not random, it means I can approximate my point very well by a rational. That's what it means. Okay, so in particular, for any rational point, if you take this random walk after n steps, then this measure of all possible outcomes after n steps of the random walk would converge in the weak star topology to the Lebesgue measure. And in particular, another corollary is that if you have a measure mu as above, the only probability measure nu, this is some kind of, fits in the general framework that Furstenberg developed to study actions of non-amenable groups. So if you have a measure nu, probability measure on the torus, which is invariant under this random walk, stationary for this random walk, with no atoms, it has to be a Lebesgue measure. So this quantitative theorem is actually, I mean, that's not, in homogeneous dynamics, quantitative theorems are not so plentiful. And this is somehow, certainly does not fall in one of the few families of quantitative results that we know. The second corollary, but not the first actually, has been extended to much greater generality by Benoit and Kwan in sort of rather well-known work. And to go back to Avi's talk, which I've mentioned several times, so actually this result here of Bourgain, Fuhrman, Modest, and myself, which relies on the discretized projections theorem and working with the real numbers, was actually used by Bourgain and Variou to sidestep a lot of number theoretic issues to prove that the Cayley graph on SLDZ modulo NZ for some set S, fixed set S mod N, generates a family of expanders where N is allowed to run over any integers, not just primes or square free or something, but absolutely any integer regardless of how it's factorized. Basically because we're working in the real numbers, and real numbers don't distinguish between 1 over 6 and 1 over a prime. Okay, there's much more to say, but I don't have much time to say. And I just wanted to end by saying a couple of personal words. I mean, Bourgain was a profound mathematician, extraordinarily sharp, quick, deep, and original. He was very competitive. I think when I got to know him well, he was less competitive than he was when my father knew him well, but he was still very competitive. But he was very generous. That sort of, people said that, but I mean, if people said it doesn't mean it's not true. He was really very generous and also very kind. I came here many nights when I was at the university as a faculty member. I came here many nights and had late night chats with him. And I mean, so I had a good time here as Princeton faculty. I sort of really like Princeton. But I think that these late night chats were, for me, the highlight of, mathematically, the highlight of my years in Princeton as a faculty member. His loss is a great loss to the mathematical community and to me personally. Okay, thank you.